friends, I am Saili Redasni, engineering student from VIT. In this video, we are going to cover topics like Introduction to Current Electricity, what do you mean by steady current, Kirchhoff's first law, that is current law, and second law, voltage law. So before starting with this, I request you to do like, share and subscribe my channel. And click on the bell icon for further notifications. Thank you friends. So, what do you mean by current? Current is nothing but when electrons are set in motion. And when electrons are set in motion in a conductor, it constitutes to current. A conductor, when we take a conductor, suppose this is a copper wire, it's a conductor. It has negatively charged particles called as electrons. They are randomly placed. And when we attach a EMF source to it, EMF is nothing but a set of batteries which lead to electric current. So when I attach EMF to this coil, electric field would be produced and this electrons will start flowing. So this electrons will flow from negative terminal to the positive terminal of EMF, while electric current flows in opposite direction of the flow of electrons. So electric current will flow in this way. So this is how electric current flows. But then, so the definition of current would be the rate of flow of charge is nothing but electric current, and the rate of flow of charge which does not depend upon time is nothing but steady current. So this is all about current and steady current. Now what is Kirchhoff's law? Now Gustav Robert Kirchhoff in 1842 stated two laws. So its first current law states as, first current law, states as, the algebraic sum of all the currents at a junction is always equal to 0. But what do you mean by junction then? Junction is a point where current splits. Right? So now take an example. Suppose this is the junction A and these are various splittings of current. So suppose from this current is coming I1. From this junction current is flowing away I2. Here the current is flowing towards the junction, that is I3. Here away I4 and here towards I5. So as per current law, the signs and conventions would be the current coming towards the junction would be considered as positive and the current flowing away from the junction would be considered as negative. So according to that, the algebraic expression would be I1, it is coming towards, so it is to be considered as positive. It is flowing away, so minus I2, flowing towards, so plus I3 minus I4 plus I5 is equal to 0. And if we simplify this algebraic expressions, it would give as I1 plus I3 plus I5 is equal to I2 plus I4. And from this we can conclude that the current coming or flowing towards the junction is always equal to the current flowing away from the junction. So this is all about current law. And this current law is in accordance with conservation of charge. Now moving on to the second law, that is voltage law. So what Kirchhoff said in voltage law. So before moving on to the voltage law, let's understand what do you mean by an electrical network. Electrical network is nothing but it is a combination of all the electrical components and EMF. So electrical components like resistors, switch. So these are all electrical components and EMF. So this combination makes an electrical network. So what is voltage law? Voltage law is nothing but the algebraic sum of, in a closed loop, the algebraic sum of all the potential differences of all the electrical components and the algebraic sum of all the EMF is equal to 0. I pardon. It states that summation of algebraic sum of all the potential differences plus of all the components plus the algebraic sum of all the EMF is equal to 0. So in algebraic form we can write as summation IR plus summation E is equal to 0. And for first current law we can write as summation I is equal to 0. Now let's understand it with a diagram. So now this is a diagram which I have chosen for voltage law. Now what science and convention says in voltage law is, if we traverse from negative EMF to positive terminal of EMF, it should be considered as positive. And if we traverse from positive terminal to negative terminal, the EMF considered would be negative. Then what is the second sign convention? That if we traverse across the resistance, if we are traversing in this way, then it would be considered as negative. And if we traverse opposite to any current, then it would be considered as positive. Now let's consider a loop from A, C, D, F, A. So now in this we are traversing from this. So here the current supplied is I1 through R2. So the direction is same. So it would be minus I1 R2. Then we move towards here. So here the current supplied is I2, but the direction of traversing and current flow are opposite. So it would be considered as positive. So it would be I2 R4. Then we are here to EMF. So it is positive to negative. So it would be considered as minus E2. Then we go towards R5. The direction is opposite. So it would be plus I2 R5. Then we move upwards. The direction of current and direction of traversing is same. So it would be minus I1 and R1. So it will be minus I1 R1. And here EMF we are traversing from negative terminal to positive terminal. So it should be considered as positive. So it would be like plus E1 is equal to 0. And now further if we simplify by taking it by taking some terms common, it would be E1 minus E2, E1 minus E2, then minus I1. In brace we have R2 plus R1 plus I2 R4 plus R5 is equal to 0. Like I have taken this term and this term together. So I get R2 plus R1, and for I2 R4 and R5. So plus I2 R4 plus R5. So this is simplified algebraic expression according to voltage law. Now second, if we consider the loop as IBEFA, that is IBEFA, the smaller one. Now we traverse from here. So I1 R2, the traverse and the direction of current flow is same. So it would be minus I1 R2. Then moving on here, from here we get I2, from here we get I1. So here the current across this resistance would be I1 plus I2, and the direction of current flow and traversing is same. So it would be minus I1 plus I2 R3. Then moving on EF2, so we get here as minus I1 R1 and then plus E1, which is equal to 0. Now if we simplify further, we get as E1 minus I1 common, R2 plus R1 plus R3 minus I2 R3, which is equal to 0. Now if we consider loop BCDEB, so that is BCDEB. Now here the direction of flow of current and traversing are opposite. So here it would be plus I2 R4. Then moving on further, here it is positive terminal to negative terminal traversing. So it would be minus E2. Then we traverse through R5. So it would be plus I2 R5. Then moving on here we are again traversing opposite to the current flow. So it would be plus I1 plus I2 R3 is equal to 0. Now these are three expressions for this loop as per voltage law. So this is all about Kirchhoff's first law and Kirchhoff's second law. In this video, what all we covered is introduction to current electricity. So current is nothing but rate of flow of charge, and if it does not depend on time, it is nothing but steady current. Then Kirchhoff's first law. Current law states that summation of I at any junction is equal to 0. That the number of electric current flowing towards the junction is equal to current flowing away from the junction, which is in accordance to conservation of charge. Then the second law is voltage law. Voltage law states as summation of all the PD of all the electrical components, that is potential difference, and the algebraic sum of all the EMF in an electrical network is equal to 0, and it is in accordance with law of conservation of energy. So this is all what we covered. In the upcoming video, I will be covering Wheatstone bridge, meter bridge and galvanometer. So for that, keep watching. Thank you guys.